Good afternoon, everybody. Welcome back to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the pleasure of having Thias Gans in our series. So Thias has a PhD from the Katholieke Universiteit Leuven, and then he moved to the Vrije Universiteit from Brussels. And then he's nowadays back at KU Leuven, where he has an ERC consolidator grant, and he's going to tell us more about such a great funding from the European Union. Thias has published across machine learning and operations research journals, and he has received also many awards, including an award on his dissertation. So we are very excited to hear more about his research, and the floor is yours. And if you have questions, I'm saying this to the audience, we can leave them towards the end of the presentation. If they are very, very urgent, then please put them in the chat, and I will read them to Thias. Thank you so much, and we are looking forward to see your research today.
All right, well, thank you very much for the invitation and for the opportunity to present our work here. So I will mostly, at the ERC grant, it only started in June, so I will mostly talk about the research that led up to the grand goal, and then in the end I'll say a bit what the grand goal of the new grant is. So in general, my research is indeed at the intersection of machine learning and combinatorial optimization, and more specifically, we look at techniques for learning from user and environment. And I'll of course say a bit more about what this is. And in this presentation, I'll present joint work with both members of my team and external collaborators. Now, I think the next slide is a bit redundant with this audience, but so when I talk about combinatorial optimization, I of course mean techniques for solving constraint optimization problems, such as vehicle routing, scheduling, configuration, graph problems, and so forth. Now, if we look at a methodology that is often used in combinatorial optimization, then it is a model plus solve approach. And then the question is, okay, where actually does this model come from? Right? Imagine and mixed into a programming formulation or a constraint program formulation. Where does this model actually come from? And then this model is typically written by an optimization expert, but to come up with all of the constraints and all of the requirements, that optimization expert in turn was in contact with a domain expert, which again got input from other kind of stakeholders and so forth. And so, in a way, this model plus solve paradigm could be seen as being very rigid and very static, because the optimization expert only formulates the model once, and then typically it is assumed that all of the constraints and the objective stays the same, and only a small part of the input data changes every day. And so the question is, nowadays with AI, with machine learning, with the capturing of lots of contextual data, what can we do to improve this process? And I would say that within the research field, there are three kind of trends. And the first trend is that some people look at, okay, can we actually learn from historic data? Can we actually learn the constraints that make up the model? And I guess this would be the least studied of the three. And the third one is, okay, can we actually use machine learning to improve the search and to find better kind of heuristics, machine learning guided heuristics, and other ways that can improve the solving and that can reduce the solve time. But what most of our research actually falls into is here the second category, and that is where we want to use learning, where we want to use data to learn the objective function. So to learn what the good or the intended solutions or the intended specifications of good solutions are. Now, the way that we look at many of these problems is that if you think about knowledge, when you create a problem specification, if you think about the kind of knowledge that there's actually two kinds of pieces of knowledge. And the first type of knowledge is explicit knowledge. And this explicit knowledge, this is knowledge that is very easy to formulate. For example, in a VRP setting, it is the number of vehicles that you have, or the distances between your stops, right? So, or even the capacities of the vehicles. So this is explicit, and this is very easy to formalize. But then there's another type of knowledge, and that is implicit knowledge. And this implicit knowledge is a lot more difficult. It's, for example, preferences between drivers, or the type of routes that they drive, or which stops. If in any VRP you can turn around the routes, right? So which one is the better one? In practice, there's typically a huge difference between them, even if you drive at night, and if all roads are bidirectional and so forth. So all these types of more subtle knowledge is implicit knowledge, and it's very hard to formulate this explicitly and to add this as rules into your problem specification. And here we have this approach that, okay, so the explicit knowledge, let's formalize it as constraints, but the implicit knowledge, let's try to learn it from data. So from this point of view, in this talk, I will talk about two different instantiations of this. And one of those, the first one, is where this implicit knowledge is actually tacit knowledge about user preferences or social conventions. Okay, and I'll give some examples in a few seconds. And the second type of implicit knowledge is where you solve optimization problems, such as scheduling problems, in a complex environment where part of the input needs to be or becomes better if you predict it from the environment, for example, demand, prices, defects, and so forth. But let's start with the first one. Let's start with the tacit knowledge. And there's one example of this, which you may have heard about already, and that's the Amazon Last Mile Routing Challenge. And so this was a research challenge. There was a collaboration between Amazon as well as the MIT Center of Transportation and Logistics. And so what they say is that, okay, in real life operations, in this case, it's delivering packages at customer locations, the quality of route is not exclusively defined by its theoretical length, duration, or cost. All right. And so in this challenge, they provided a large amount of data, more than 1,000 instances, where they had a list of customers that had to be visited, and they were grouped into zones. It was across a very large geographical region. And then they also provided solutions, so TSP solutions, so routes, with a label saying this was a good route, this was an average or a bad route. And this labeling here was from a driver point of view, or at least from a domain expert point of view. And so the challenge was, can you actually learn what kind of routes are better, and can you use that to find these routes from the go? And not simply using theoretical length, duration, or cost. Now, this challenge was fairly recent. It concluded, I think, a few months ago. But we've been working on a similar setting since 2019, but then for vehicle routing. So not for TSP, not for traveling salesman problem, but for vehicle routing. And this was a collaboration with a company. It had only a small number of vehicles. But what the situation that they were in is that they had route planners, obviously, that used route optimization software. But then the solutions that came out, they always tuned the results. They always started changing the results. And that they always had some kind of reason for it. For example, they would say, yeah, it's better to offload the larger goods at the beginning of the route, but it's also better if the drivers, if they end their tours at about the same time, because then they can have a coffee together. And some clients, it was better that they were visited earlier, but it was not a hard constraint. And so they had all of these kind of preferences that had to be traded off, and based on which that they made manual changes. And so the question, as artificial intelligence researchers, the question that we ask there is that, can we, instead of eliciting all of these preferences and adding them to the objective function and hand tuning this, can we actually use machine learning to learn what some of these hidden preferences are, so that the number of changes that they need to make to these routes becomes smaller, so that they, or even zero, but in practice just smaller, before they send it to the GPSs of the drivers. And if you would succeed, it will actually ideally be adaptable to changes over time. Now, a first side note here is that this is actually small data, and within this setting it will always be, because in this case, we had 6 months of data, which from an operational perspective is actually quite a lot. But 6 months of data is just 26 weeks. And that's just 130 weekdays. So they drove out once per day, actually per night. So it's all, from a machine learning point of view, it's only 130 instances. But from an operational point of view, it's already half a year, right? So that's to be taken into account in the techniques. Now, in our initial work, we actually, because I did my PhD in data mining, you didn't mention this, but so I have a background in data mining. And in data mining, there's a large number of literature in the mobility mining literature on, for example, driver turn prediction or predicting the stop location and so forth. And so this was about single vehicles. For a single vehicle, they learned to predict where a truck would be going or what its destination was. And they often use Markov models, Markov techniques for that. And so we asked, well, can we actually use similar kind of Markov models, which can work with small amounts of data, to learn the preferences not for a single vehicle, but actually across the entire routing. So not the preference of one, but of the actual planners. And if so, can we optimize over them? Because this was a vehicle routing problem with site constraints, so we wanted to be able to put it into the solver that would continue to respect the site constraints. And so one of the key ideas is that we actually want to estimate the probability that a certain routing, so across all of the vehicles, is going to be preferred. Yeah, so that would be the one that the planner would make by hand. And in order to make this more tractable, and we can look at a first-order Markov approximation, that means that we estimate the probability as being the product of, well, starting at the depot, which is always the case, and then you only look at, you have this Markov assumption that you only look at the current stop to determine the probability of which stop you're going to take next. So the probability of taking stop 2 given stop 1, stop 3 given stop 2, and so forth. And so this is a first-order Markov approximation. And if you take this Markov approximation, then the challenge now remains to estimate the probabilities of these transitions. All right. Now, so the one way to get these probabilities is that you can use a counting-based approach. For example, we can look at how often in the historic instances from client stop I to stop J, that arc was actually taken and divided by the number of routings in total. So this is a fairly standard way, counting way to build such a first-order Markov model. And so, okay, so that's one approach that we could use. But how do we plug it into vehicle routing problem then? Well, as I said before, a key idea is to look at it instead of a routing problem where we want to minimize the total distance, look at it as a routing problem where we want to maximize the likelihood of the solution. And in this first-order approximation, it's this product. Now, a very standard thing to do when working with probability, that the product of these probabilities is actually so maximizing the product of the probabilities is the same as maximizing the sum of the log probabilities. And that means that you can actually use a standard VRP solver to maximize the probability of the route under this first-order assumption by making it, instead of minimizing the distance, make it minimize the minus log probability. Okay, so we have a way to get the probabilities, and we have a way to feed them into any existing VRP solver and have it compute routes for us to find the maximum complete route. But now let's try to do better, okay? And that is, let's understand the data generation process a bit better. So the training data is actually not a training set, as is typically presumed to be the case in machine learning, but it's actually a sequence. So every day they make a routing, and then the next day they make a new routing and a new routing and a new routing. Now, if you think about the process that a planner goes through, then you know that they actually learn from day to day about what good routes are. So there is a sequential nature in these routings. And that's the second point here, the last point here. So the preferences that they have, they can change over time, both because they learn or because the operational characteristics at hand change. And maybe and gasoline prices are rising, so maybe suddenly distance becomes a bit more important, or maybe they lost some customers, or they have a new customer, they want to make him super happy, and so so this kind of preference can change. That's one thing. And the other thing is, maybe that I want to stress, is that in this case, every day we're not solving the same vehicle routing problem. Every day the set of clients that need to be visited is a subset of the whole client file of the company, right? So it's always over slightly different sets, but the preference can change. And actually, if we analyze the data, we clearly saw this, is that there was a company change at around this week, where the set of customers that they had shrank and changed quite a bit. So this is the kind of concept drift from a machine learning point of view, where different kind of IDs are typically used by the planners. So can we take this into account? Can we take this sequential nature into account so that we can actually adapt over time? And if we focus on the aspect of the concept drift, what we can do is that in our initial approach, the standard Markov counting approach, we don't take into account how long ago that the historic solution was. But there's actually ways that we can do this. And in machine learning, you look at it as being a prior for each of the historic instances. So each of the historic instances have a different prior about how likely or how important that instance should be in your learned model. And more mathematically, it just means that you're going to weight each of the instances. And so whether or not that arc was taken is multiplied by the weight, the importance of that specific historic instance. And so some of the options here are, you can either use uniform weights, and that was the initial approach, or you could weight by how similar the stops that you need to solve for today are to the historic instances. So the historic instances that are more similar to today would get a larger weight than the ones that are least similar, for example. Or to handle concept drift, you could sort them by time, weight them by time, meaning that the more recent ones are more important or have a bigger influence on the probability than the older ones. And so this is what we did. And actually, so maybe it's important so instead of looking at the data as a data set, we look at it as actually a time series, so to say, right? And in time series analysis, there's this concept of exponential smoothing, which is used a lot, and also we can determine these weights using something like exponential smoothing. And what we saw is if we use our model in a sequential way, so we up to day X we use the data that's available before it, and then the next day we use all of the data up to the day before it. So it's like a sliding, an increasing backwards horizon approach. So in that case, we saw that this weighting makes a big difference, and especially the exponential smoothing is the most beneficial. So here, that's before there was this concept drift in the company data. So before, it doesn't really matter because the concept is still the same. But after the set of clients is reduced, the exponential smoothing algorithm is the quickest to pick up, to differentiate what the old preferences are for versus the new preferences. And also, if we reverse this, that's the bottom line, exponential smoothing works very well. All right, now, when I've presented this work before, especially to an OR audience, people said that, you know, you're learning the preferences, but if you're doing this, you're basically mimicking the user choices, right? You're learning to copy rather than learning to make intelligent decisions. And in OR, the whole point of solving software is to make intelligent decisions, to do better than what a planner perhaps could. And so optimization software is meant to do better than the user. And why? Because it can consider more candidates and resolve conflicts and so forth. And so actually, if you talk to these planners, then they typically have a reason behind what they say, and they do keep the total distance into account. For example, they say that I prefer route X, even if it's 2 kilometers longer. So we notice that internally they keep trading off their kind of preferences that they have with the impact it has on kilometers. And so in practice, what we actually recommend and did was we took a linear combination of both the preferences that we learn and the distances from the distance matrix. Okay, this gave the best results. So to conclude this very first part of this multi-part presentation. And so if we turn it into this maximizing log probability, you can use any kind of VRP solver. And with the exponential smoothing, it's actually better than other types of approaches. Now, this is already from 2019. So we've since then, we've also looked at whether we could use neural networks for this, because we like them and because it's trendy and lots of other reasons, but it's challenging, okay? And some of the challenges are that even if we stick to our first order Markov assumptions, we would need a network that predicts n times n preferences, right? Because it's in our preference matrix we have, okay, if you're at stop I, what's the chance that it will go to the first stop or to the second or the third or the fourth? Okay, so you would need n times n outputs, which is a lot of outputs. I mean, it's not a problem, right? It's quite a bit. Another challenge is what kind of input representation would you use? And so there's a different number of stops every day. So how do you encode this variable amount of stops? But you also want to use the distance information, because that's still a basis for making decisions. So you need to encode at least n times n distances. And we know that the exponential smoothing, for example, works really well. So you also want to encode all of the historic instances into this neural network. And then what loss function to use is also a question, but the main point about this one is that there's only very few data available. So if you would just put a fully connected network on all of the historic data and make it output n times n predictions, you're going to overfit massively, and it actually performs really bad. And we know because we tried it. Okay, so how can we do better? Well, the first key idea is, well, we want to have a network with fewer amounts of parameters. So let's do parameter sharing. And the simplest form of parameter sharing is just to share an entire subblock of the network. That's to say, more specifically, we're going to learn one individual network. And this network, we're going to apply it on every source stop. So this network for a source stop would predict the probability to each of the other possible destination stops. Okay, so now we don't need a network that predicts n times n outputs. We just need one network that predicts n outputs, and we're going to apply it to each of the stops, and actually only the relevant stops, so that's an added benefit. Okay, so parameter sharing, single network with length and output that we can apply on each of the stops. The second key idea is to use a domain-specific architecture. So you want to encode all of the distances and the historic information, but a simple approach would lead to too many parameters. And actually, we tried a lot of things, and then we said, okay, no, this doesn't work. Let's take a step back, and let's look again at what worked well in our previous work. And in our previous work, we actually took a linear combination of the preferences that we learned, that is this Markov, exponential smoothed Markov counting, and the distances. And within neural networks, there's a stream of thought called unfolding, where you actually look at the existing mathematical and formulate them as a neural network. So you can do the same here, and it's very simple. Was somebody saying something? No. Okay, so this is how you can express the exact same formula, but then as a neural network. Namely, you take the Markov probability, for example, the log probability, you combine them in a linear layer, and then you make it out, and it will output a value for each of the destination stops. You put a softmax on it, and then you have our predictions for each of the destination stops. Now, if you share this linear layer across that dimension, you have exactly this setup. So, and you would have just two coefficients here, and they could be rewritten to beta. So that's kind of the simplest possible neural network that you can construct. And I can guarantee you it does not overfit. It basically just trains the beta parameter that's best given the data available if you have a suitable loss function. Now, of course, and so this started working fairly well. So the real goal was to include contextual features. And for example, the Markov counting approach can take into account what day of the week it is. But we know that what day of the week it is can have an effect, but also what the other stops are. And so the final kind of architecture that we used, it used embedding layers for the stops, and so the variable size number of stops, and for the weekdays, so it can learn its own embedding. All of that combined in a layer, and then a softmax on top. So that's actually a fairly good approach. I haven't said anything about the loss function yet. I don't have too much time for it, but I think a very nice observation is that you can actually use a classification loss in this case. So as I said, the network takes a source node and all kinds of contextual information to account, and it will make a prediction for each of the possible destination nodes. And one of those source destination pairs will be the true one, will be the preferred one in that historic solution. As you can actually see that as a multi-clause classification problem, you can use an existing multi-clause classification loss, such as negative log likelihood, and that's actually a good proxy for the arc difference, which is the number of changes that the planner has to do to turn your solution into the one that he prefers. And so if we look at different kinds of measures, and so the previous approach was fairly good, but with our neural network, if we at least removed one part of it, we were able to do slightly better. And this is much better than using a distance-based approach. And another nice point, and so this is some evaluation of quality, you can say. But what's also nice is that with this neural network, it learned to trade off the preference versus the distance a bit more. And so this is the very smallest distance that you could get. This is the one if you use the pure Markov approach, and the neural net better satisfies the preferences. That's what these numbers say. But it also is a slightly shorter tour than this one. So for details, I have to refer you to the paper, which will be presented in 2 weeks. Okay, and so that's a first example of implicit knowledge that we can learn from data. Now the second example, so it's time for end-to-end learning. So what we did up to now is we learned the preferences purely based on the data up front, and then we solved in a second phase. But we're now going to look at techniques that do both at the same time and why they need to do that. So again, a bit of a motivating example, or the problem setting that we are looking at here. And so it's called, in literature, for example, prediction plus optimization, sometimes called decision-focused learning. And the key idea is that you have part of the input. Let's say that your optimization problem is a scheduling problem, and part of your input needs to be inferred from historic data. For example, you want to solve a scheduling problem, and you want to minimize total energy consumption, total energy cost, not consumption, total energy cost. But if you're a large enough industrial player, you actually don't know what the energy prices are going to be. So you need to predict them up front in the day ahead market, so to say. So for each of the coming hours, you will need to predict what the energy price is going to be at that hour. And then you're going to solve a scheduling problem over this full batch. So for the coming day, so for the full set of predictions, you're going to solve a scheduling problem in the hope that it minimizes the total effective cost. So a key characteristic is that the prediction is doing multi-output prediction. So it's predicting for every of the coming 24 hours of the next day. It's making one prediction for every individual hour. So you have 24 predictions. And a second important characteristic is that the scheduling problem here, that it is a discrete optimization problem over the full batch of predictions. And so it's not some kind of sequential thing where you just need to decide at every hour. No, you need to decide upfront for the full day over all 24 predictions. So some other examples of such setting, for example, in a steel plant production, you need to schedule the production schedule of the next day, but you want to make prediction about what goods might have certain defects and adjust your schedule, for example, your after process based on that. Or another case that we talked about with a company, they are doing money transportation, but they don't know how many coins there are, what the volume is at each of the clients until the client calls. But they typically call on Friday, so if they could estimate the amounts better, if they could estimate it earlier, then they can do some preemptive routes and not be in trouble or having to reject clients on Friday. Okay, so right, if we could apply the same kind of approach as in the previous part of the session, namely we use some kind of machine learning technique to learn and to predict each of the, for example, energy prices, and then feed that into a MIP solver as if these were the real prices and get a solution. Now, of course, we've tried that, and many others, actually, this is often used in practice also. But if we look at what happens is that this is a typical example where in green it's plotted what the mean square error is, and so you see that as you train the network, the mean square error continues to decrease. That's a good thing, but the regret, and that is the regret here, is the cost that you pay when you actually would execute the schedule coming out of the optimization. So this is the task loss, the cost that you have after solving and executing the schedule increases. And you might say, yeah, but this is a typical kind of graph that represents overfitting, but this is not about overfitting, because this graph is plotted on the test data, so unseen data. Now what is going on here is that the mean square error loss function is actually not informative enough. So it's not a good proxy for the task loss, for the effect that the errors of the prediction have on the optimization, for the regret. And another way to think about this is that, as I said, this is a multi-output prediction problem. So our predictions are a vector of prediction. Now, mean square error, what does it do? It averages the individual errors of the entire vector, right? And it does this the same way for all of them, so uniformly across all of the predictions. But if you think about what the scheduling is doing, what the mixed integer programming here is doing, is that it's doing joint inference. It's trading off the different kind of predictions and making its decisions based on that. And so that means, because it is a joint inference, that actually it has a joint error, or in other words, some errors are worse than others. And the mean square error doesn't capture which of the errors is worse than the others. And so if you listen to his explanation, you'll probably say, oh, let's just find out which ones are the worst ones and which errors matter most. And that's where it becomes really tricky, because which errors are worse is determined by the combinatorial optimization. So it is a combinatorial problem. It will be those for certain values, but it will be those for other values. And so you actually need to call the solver to know, given that input, what elements actually have an effect on each other. And so that means that we cannot take shortcuts, and we have to somehow be able to use regret, and so the output our error after optimization, as a loss function, and do that in an end-to-end kind of training way. But this is a very challenging problem for multiple reasons, and the argmin here, so solving it for just one instance is actually, so if you given the predictions, so V here is the predictions, so C, the cost factor, C is the predictions. So given the prediction C, it could be that there are multiple solutions that are optimal. This is one of the smaller problems, but still important. Another problem is that the full possible set of solutions is implicit, and it's actually exponentially sized. So although this is an argmin, you cannot use a softmax. And what you typically do in machine learning, if you have a maximization problem, you take a softmax, but because it's over an exponentially sized number of problems, this isn't possible. And computationally, just computing this argmin means solving a scheduling problem or solving some other kind of mixed integer programming or constraint programming problem, and so it may be NP hard. All right, so it's a really fascinating problem, and in the last number of years, people have looked at it with really interesting results at the combination of the two research fields. So I'll highlight a few, and the first one is that let's maybe formalize it a bit more. So the thing that we really want to minimize is we want to find the network parameters, assuming a neural network, and the network parameters such that the regret, that means calling the optimization given the predicted cost factors versus using the true cost factor, that should be minimized, okay? And you can formulate this as a bi-level optimization problem, And so you want to minimize network parameters. You have n examples. You really want to minimize the regret, but to compute the regret, you need to solve the optimization problem. Okay, and so these challenges remain, and actually there's no explicit gradient that you could use in mixing if you want to do gradient descent-based learning either. But given that it's a bi-level optimization problem, you might say, okay, let's do bi-level optimization. Okay, now even if you assume that f is linear and that v, so the set of all possible solutions, is continuous, and so that means that this argmin problem would correspond to solving a linear programming problem, you still have the case that the solution is not unique. And so the solution is an element of argmin, it's not unique. And that means that you need to add another assumption. Typically, you have two options. The pessimistic assumption assumes that argmin, if there are multiple equivalent solutions, will return the worst. But that means that formulating this explicitly becomes a tri-level problem, which is even less attainable. And if you take an optimistic assumption, so that means that if there are multiple equivalent solutions, you take the best one. If you do that, then the machine learning model will be smarter than you are, and it will start predicting. Solutions that are supposedly equivalent, and so it will misuse this optimistic oracle. Now, I think one of the nicest pieces of work that has emerged in the recent years, and it was released on Archives in 2017 and accepted in Management Science in 2021, is that of the smart predict plus optimize loss by Elmar Tupan-Grigas. And so what they actually do is they define an upper bound on this pessimistic loss that is convex. So they have a very nice proof of it. And what I think is, or at least for us, had the biggest impact of this paper is that they can define a subgradient based on this convex approximation. And it's actually fairly simple. You take the true optimal solution, and then you subtract the optimal solution under a perturbed cost factor from it, and that is your subgradient, and you can use gradient descent learning. Okay, so that's really nice, but what I think is the key part of this work here is that they don't just solve for the predicted cost vector, they actually perturb them. So they don't solve for C, which is but they take a perturbation of 2C minus C star, and I think this is one of the ways to avoid the situation where you have multiple equivalent solutions. And so if you look at it long enough, you will realize that it amplifies the errors of the predictions, and by that way it avoids abusing equivalent solutions. So that so if you're familiar, or at least basically familiar with machine learning, this is how you can write down stochastic gradient descent. And so you sample a batch, you do a forward pass, you compute the loss, and from that you get the gradient, and then you update the network parameters through backpropagation of that gradient with some step size. Now with this SPO approach, there's only a minor modification to the gradient descent learning, namely you still do your forward pass, but now you perturb these predictions, and what I like to call the SPO trick. You perturb the predictions, and you need to call a solver on these perturbed predictions. But then, given the solution of the solver, you can define the subgradient, not the gradient, but the subgradient based on that difference, and then you do the standard backpropagation mechanism. And so, a fairly simple or fairly elegant, I would say, modification. Now, even with this, what now happens is that you will need to solve a combinatorial optimization problem for every training example. And so if you do 10 to 15 epochs with 5,000 samples, you're in for a very long waiting time. So let's look at how we can reduce the solving time. And so one of the things is that you will need to solve this argmin problem over and over and over and over. Okay. Now the constraints always stay the same, so only the cost factor stays the same. Right? And that means that if we solve for thousands of C values, each instance might have a different optimal value. But if you think some more, and let's say that the problem is a mixed integer programming problem, you will need to solve the same problem over and over again, but mixed integer programming itself actually repeatedly solves a linear programming problem. So maybe you don't need to solve the full MIP problem, we can just take the continuous relaxation and solve the LP problem. And we can even go a step further. If you're going to solve thousands of LP problems, well, each one of them repeatedly finds an improving basis. So maybe we can just start from the previous basis and only have it do these kinds of basis updates. So by looking a bit deeper at what's going on in solving, we can actually improve the runtimes quite a bit, as we use these relaxations and the basis tricks. And then instead of having an epoch-based timeout, we can actually give it a time budget. And we say, do as many solves as you can, and backpropagates, of course, within 2 hours or 4 hours or 6 hours, which is a more manageable way of training in this setting. All right. Now, there's a number of related works in gradient descent-based learning. And so I've mentioned SPO+, but there's another approach called black box, which also does some kind of perturbation, but it does 2 solves. And there's another family of methods that don't work with a subgradient, but that work with implicit differentiation. And I'll shortly highlight a few of these. So these black box methods, they do not make any assumption on your solver. They just call a solver and use the output from that. But the implicit differentiation techniques, the white box differentiation techniques, they do. So if we know, for example, that it's a mixed integer program, can we get better gradients? Now, can we compute the gradient of a MIP? Well, it's a discrete problem, so no, it's non-differentiable. Okay, then can we maybe compute the gradient of an LP? Well, it's a linear objective, so you can take the first derivative, but you can't, and the second derivative will be 0, so it's not invertible, so it actually won't be usable in your gradient descent-based learning either. But what if you would have a quadratic program? In that case, yes, there's a very nice result, also from 2017, from Amos and Coulter, that show how to do implicit differentiation over QPs. And so this is a standard formulation of a quadratic program. You can take the Lagrangian relaxation from that, and then you can actually differentiate the KKT conditions. I'm not going to go into the detail, but I think it's a beautiful paper, and they show how to get the gradients from a quadratic program that you can then use for gradient descent-based learning. And so at IIII 20, you have these authors that actually made this observation. Okay, so you can do it for quadratic programs, but not for linear programs. So let's make a linear program a quadratic program by adding a quadratic penalty. And then we can use the same kind of techniques. And so actually, there's much more in the paper, of course, but that's the core idea, and it worked. Okay. Now, when we were looking at this, we were wondering, would we actually add some kind of rather arbitrary quadratic penalty, like 2 norm squared of x? If you think about the kind of solver that you can use for mixed, and you have simplex-based or you have interior point-based methods. But interior point-based methods, they actually have been using gradients and steps in the gradient direction of a linear program for many, many types of years. And so we started to dive a bit deeper into this. And what the interior point solvers do is they actually add the logarithmic barrier, a famous concept. So they don't add this arbitrary x squared, but they add the log of the x's because it implicitly enforces that x has to be positive. Now this is still twice differentiable. This still has twice differentiable KK conditions. And another added benefit is that you don't need to set the gamma parameter up front, but interior point solving itself actually will gradually reduce the lambda parameter. So it's a more principled way. And actually, we can integrate this into an end-to-end kind of approach. And so we take the predictions, even if it's a discrete, so an ELP, we can relax it to an LP. Then if we look at what these interior point solver methods do, is they actually solve the homogeneous self-dual embedding. They do lots of Newton steps, decrease the gamma and so forth. And we can actually stop at some point and then compute the task loss from this. So here we would differentiate this homogeneous self-dual embedding and get the gradient from that. And this works really well. And so we did a comparison. And do we differentiate the KKT conditions, or do we differentiate the more stable formulation that's used in these interior point solvers? It's actually better to do the latter. And then we also compared to SPO, for example, and to the quadratic programming approach. All right, and so this was presented at NeEDS. We presented it at NeEDS last year. All right, now Yeah, so far so good. I still want to highlight one. I know I still want to highlight one kind of technique, which is a very different kind of technique, but also very elegant. So the previous approach was very operations research centered, but we also had a very machine learning centered look at this. And here we looked at the challenge that V, so the set of all solutions, is actually implicit and exponentially sized. Now, in machine learning, there's actually a large number of problems where the number of output clauses is huge. And so in our case, it's the exponential number of all possible solutions. But in other fields of research, like in language or in probabilistic inference, what they started looking at is contrastive losses. And for me, the key idea of a contrastive loss is that it turns an n-ary argmax with a potentially large n into n-1 pairwise argmaxes. And then it only subsamples sums. And so for decision-focused learning, what you do is you only take a subset of the solutions, and then you look at the pairwise difference between the values that these solutions get. So that's the first kind of idea. I know I can't explain too much, but we can apply the concept of contrastive losses also in a decision-focused learning setting. And then the second key idea here is that all of the current methods and these white box methods, they actually use the continuous relaxation to make it non-discrete, which puts you already quite a bit closer to your goal of getting gradients. Now, if you look at what an LP relaxation does, then you could call it actually an outer approximation of your true problem. But because the constraint stays the same, also the polytope stays the same. So we might want to take an inner approximation, and an inner approximation is, in this case, is a convex hull of previously computed solutions. So instead of calling the solver each time, what we can do is we can maintain a pool of known solutions, and that pool is actually an inner approximation, and we can subsample from that to get our contrastive loss. And so the main advantage here is that you do not have to call the solver each time. And we can, for example, grow, and we can have a 5% policy where we, in 5% of the time, call the solver, and in the other 95% of the time, we just use the previously computed solution as the inner approximation. So this is both fast and good. Actually, we can apply it. We can apply this idea on SPO, on black box, any other kind of methods, or we can do our noise contrastive loss functions. And so in all cases, the training time is drastically decreased, and the regret stays about the same. And so in some cases, the reduction in runtime, if we do the solution pool caching, is actually really huge. Okay, all right. So let's wrap up here. And so the key idea of a lot of what we do is this difference between explicit and implicit knowledge, where we use a solver for the explicit knowledge and we do learning for the implicit knowledge. In many cases, that means that the problem will become a maximum log likelihood kind of maximization problem. And it's very good to keep going back to both the machine learning and the solving side because they both typically can be improved. And so actually this end-to-end prediction plus optimization is starting to become possible. Even runtime now can be controlled. Lots of future work. So I was going to shortly say something about this ERC project. So in this ERC project that I have, it's a 5-year project, and it's about conversational human-aware technology for optimization. So the vision here is that we're starting to make solvers that can learn from the user and that can learn from the environment. So if we push this further, then the kind of thing that ideally I believe that we would want is a solver that can learn from us, but that we can also talk to, that we can converse to, and for example, ask for explanations or let it be stateful with the kind of interactions that you have. And so this is what it could look like if we would have it in a chatbot version, but the project is not about the natural language processing. I think that's advancing pretty amazingly rapidly on its own, but rather what kind of optimization technology, what kind of capabilities do the constraint solvers, the combinatorial optimization solvers need to enable this? And I believe the first basic components is that it must be able to learn, and I've highlighted some of the work we're doing in that direction. And then the next part will be making it more conversational and stateful. And so I believe this can really be a paradigm shift in the way that we use combinatorial optimization solvers, but it does require a specific unique combination of data science and optimization. And actually, I'm hiring postdocs, so if you have a relevant expertise, I would be happy to talk some more with you. And that concludes my talk. Thank you very much.
Thank you very much for this very, very nice talk. I would like to now open the floor for questions from the audience. So you can raise your hand, and then yeah, we will give you access to the camera and the sound. Yes, so we have Jan, yeah, from Vienna. Nice to have you today here, Jan. So Christina will give you, yeah. So I believe that you're
does
now...
it work?
Yes, it does work, yeah.
Okay, thank you very much, everyone, for organizing and also for giving this interesting talk on the interface of, let's say, optimization and data science. So I have maybe two questions, but just start with one. In the first part, you mentioned, and also in your ERC proposal on the last slides, you mentioned you want to learn the preferences from planners. So to say, not only look at a very simplistic objective like minimizing distance, but trying to learn this implicit knowledge what planners prefer. And is this limited to planners, or do you also analyze data what customers prefer, and how you include that?
I guess it depends on the definition of customer or planner. So if it's a software company that sells VRP software, the customers are the planners. But in general, what we look at is what solution is actually executed on the floor. That's the perspective that we. So in the VRP setting is what is sent to the GPSs of the drivers. In a steel scheduling setting, it would be what is actually the plan that's given to the operators and to the machines. And from that, we want to learn these implicit preferences. So we don't model a user per se separately, but we look at it from a solution perspective.
Okay, now that I understand it, maybe the follow-up question is there also the idea that you could learn things that should be avoided because of bad manners or situations where you think planners always did it like that, this is why they like it, because you know that yourself in combinatorial optimization, we sometimes suggest things that planners don't understand, and this is why they don't like it. Yeah. And yes. So where do you draw the line between learning what your example showed you, like we all learn from our teachers, yeah, but sometimes maybe our teachers are also not perfect.
Yes, absolutely. So in a VRP setting, we actually mix the preferences that we learn with the distances, so that and typically it's only like 10% for the preferences and 90% of the distances. Turns out to be quite good, meaning that distances still have an importance, and it's more like in the fringe on almost equivalent solutions that the preferences will come into play. But your question goes a lot deeper, and I think there's two aspects to that. So the first one, on the more positive side, is that if you talk to planners, for example, in a scheduling setting, then they are not always willing to formulate the things that they take into account. And so there might be, if one person just comes back from a burnout, they will reduce their load, but they're not going to tell you that they're favoring that person. Or maybe somebody has an influential position and so gets fewer weekend shifts, but nobody's going to actually tell you, please encode that that person should get fewer weekend shifts. So in that case, I think some of these preferences can be learned. Now, the trickier one is the one that you asked about. What if they have certain behaviors built up over the years that is limiting the quality of the solutions that can be found, right? And the current method would learn that. And I think we're going more in a bit of a psychological direction here. So I think the right kind of thing to do is to trade off some objective function with a more subjective function that we learn. But on the other hand, we're talking to a company in the steel industry, and they're saying that in some cases, the client will reject whatever fantastic optimization software they have if it doesn't at least follow some of the current mental models of the planners. And so is it desirable or not? I don't know, but I think the mixing is the mathematical answer to that
Okay.
question.
So Dolores, you can stop me when I am talking too much. But anyway, so there's just one comment on, because I like this idea of mixing, and it reminds me of a visit to an Amazon last mile hub or whatever they call it, where they told us, okay, so they have some kind of machine learning in terms of times they have to plan for visiting like actual customers. And the new employees always try to rush through to make a good impression. And the old colleagues tell the new colleagues, don't be so fast, the machine learning or our computer will learn how fast you are, and you can't do that all your working life. Yeah. So this is why I like that you have this, let's say, mixing a little bit. Of course, there's implicit knowledge, but of course, we also optimizers know that you can, I would say, over-optimize, if you know what I mean, because your plans
Absolutely.
need to be feasible not only today, but also tomorrow. And they, of course, should be improvements. So that is a very interesting line you're going between these two worlds of what you benefit from learning and what you can benefit from optimization. So that is very interesting to me. So thank you once again.
Right. Thank you for the question.
Thank you, Jan, very much. Do we have any other questions from the audience? And as I said, if you raise your hand, then we will unmute you, and you will be able to share the camera. So Tias, you rely on a solver, right? On what the solver is doing, but would you be able to so learn, say, a kind of rules that will help, say, avoid using the MIP solver all the time, but rely, say, on heuristics that will give good solutions?
Yeah, so that's more in the direction of learning to solve. So learning heuristics that guide the solver, or like a meta-heuristic solver, for example, to the right solution. There is something in the middle, though. So what we see is that if we, in the VRP case, if we solve over the distance matrix and we use an exact solver, as you know, and scalability can be limited. But if we learn these probabilities, and so they are automatically between 0 and 1, and if we add in the preferences that we learn, then the solution becomes, not the solution, sorry, the distance matrix or the probability becomes a lot more sparser. So it kind of like pushes things closer to 1 and closer to 0. And because of this sparsity, actually the solver becomes a lot faster as well. So our work is not focused on making the solver faster or guiding it to the right solution, but we do see that from this probabilistic point of view, it kind of sparsifies the matrix, and it does increase or decrease runtime.
Yeah, I was not necessarily trying to do, but I like what you said about the sparsity, because that's something that we work a lot on. It's not necessarily making the solver faster, but find certain rules that would allow me to say, well, I can construct the solution following these rules, and that actually that's not very far away. But I guess that's what you are saying, that if I have this sparsity in the distance matrix, maybe it's I could go for trying to define those rules with the sparsity. Yeah, thank you.
So in learning to solve, you can imagine that they also learn this kind of probability function, but then the idea is that if you just use some greedy algorithm to make choices, that you find a solution quickly. So yeah, so we don't. I understand the point of view, and there might be connections. But we often assume that you have other hard constraints, although they could be encoded if you,
yeah. If you have more constraints that you want to implement, of course, those rules may not work. Yeah. Thank you. I have a question from Belen, so we will unmute you, and you can share your screen also. It takes a bit of time, sorry. Yeah, Belen.
Hello.
Hello.
Yeah, thank you. Thank you for the talk. It's really very interesting, and it's amazing how many, techniques and how deep you know all the techniques in both sides, the optimization and also the machine learning. So the broad knowledge of both things is very, very nice, and the way you combine them. Thank you for that. Just to follow up the talk about the VRP problem that you presented. I wonder, like at the beginning, you started with this assumption of the Markov change, basically, like it's
Yes.
basically a bit like just depending on the next step.
Yeah.
Is that very important in kind of like the whole thing? Does make a big impact if that's not the case?
So we took that assumption because we wanted the objective to be the standard combination of arc costs. So we wanted to learn something at the arc level. And so we actually have also learned a second order model, but then it doesn't become a linear objective, but a quadratic objective. So you need to use quadratic programming solvers, and that slows down the solution approach up to a point that you sometimes don't find the right kind of solution. And so even though your probabilistic model becomes finer grained, using it in a solver becomes much more difficult. So you think you win at the probabilistic level, but you actually lose at the inference level and on the whole pipeline. At least in the work that we're doing where we have these hard constraints. That's one thing. And then one part of our motivation of using the neural networks is that even though the output is at the level of pairwise preferences, actually the input, we can give it the full set of stops. So it could learn correlations between the other stops that are present and one pair, but it's not the output of the probabilistic model that contains it. Like it's still this first order model, but it can use higher order information if we encode it in the features.
I see. Okay, thank you. Yeah. Another question is like for the other problem, the one, for example, where you have the energy prices and the estimation of the energy prices. I didn't get at the end, when you are taking into account the energy prices and the losses in the reject function. How this uncertainty is taken into account? Are you trying to kind of like average on the different, so it's kind of like an expectation, or is in kind of like some kind of
all right, so we actually want to predict a single cost factor and optimize over that as if it is the true cost. So we don't do a stochastic optimization over possible cost factors, but we want the individual cost factor to be more suited to the task, to the optimization problem. So it's still a standard prediction problem. We get a single list of outputs, but but the machine learning part, that one is trained using the output after optimization.
So at the end of the day, you do better. It's basically you are doing better in the real data.
In terms of regret, so in terms of the cost,
yeah,
the energy cost, for example, that you would have to pay if you execute the schedule on a test set.
Yeah. Okay. Yeah, there is no like nothing that you take into account the variance of this regret or anything.
No.
Kind of like,
well, I mean, we have a test set, and that's over.
Yeah.
You can talk about the variance on the test set, but the solving itself takes one cost factor and solves one combinatorial optimization problem.
Thank you.
Thank you very much, Belen, for your questions. I ask one more time, is there any other question from the audience? Jan?
Yeah, sorry, it's me again.
No, we are very happy.
Maybe a quick one. So you, especially in the first part, you mentioned those metrics. For example, I forgot what the name of the metric was, how the solution changes or is different from what the planner prefers. Yeah.
Yeah. So arc distance and root arc difference and root difference.
I'm really in love with those metrics. Yeah. And the question is, can you use it for, let's call it explainable AI, to let the planners trust more in your, let's say, from a planner's perspective, weird combination of distance and what they like, because the outcome might still look weird to a planner, right? If you're mixing it, whatever percentage is it is, yeah. Can you show them this score? Have you ever thought of visualizing it? Because I like this. I use this a lot in meta-heuristics research of showing how diverse and different my solutions are. Of course, only internally, but maybe that's helpful for explainable as AI as well. I don't know. Yeah, I just saw that and thought about it.
That's a good. Yeah, thank you. That's a good question. So we are looking into explainable optimization as part of this, or we will, but it doesn't really go in that direction. I think in terms of the arc difference, we need to be able to compute the arc difference with respect to a solution that they prefer. So showing it to the user is a bit difficult if they haven't told us yet what the solution is that they actually prefer. But I do understand the idea that if we could somehow explain that in retrospect, the number of changes, but I don't think it's very interpretable. So I don't think it would really achieve the goal.
Yeah, I haven't thought about it in detail, but just was inspired by your talk to think about it a little bit.
Yes, so the evaluation measures and which measures to use to learn the preferences over, that's actually an extra dimension. And maybe even the comment about the logits, like can you learn some kind of rules? Could be, can you learn some kind of sub-objective that they didn't know about, but that is actually able to make the difference between what a good solution is according to them and what a bad solution is according to them. So.
Exactly. And the problem is, if you know that objective, would they realize that that is their objective? Yeah. So it's implicit, right? If it was explicit, you could model it right away anyway.
Yeah. Yes.
Interesting topic still. Yeah.
Yes. Yeah, we work a bit on constraint learning, and there's a bit of that, but it's much younger than what I've presented here. So.
All right.
Thank you, Jan, very much for your questions. Is there any other question from the audience? Yeah, if not, we will close it here, Tias. You can see that you have had a great audience with great questions. So we are very happy to have had you over here. And the video will be soon available on our YouTube channels, and you will have even more views. Thank you very much to you for coming today, and thank you to the audience for coming back, and see you soon.
Yeah, thanks a lot for the opportunity and for staying around.
Yeah.
Bye.